Hello students, welcome back to Electromagnetic Field Theory. In today's lecture, we are going to talk about, let me check, we'll be talking about Poynting theorem, okay, and Poynting vector. Now let us see what are the prerequisites that are required. Maxwell's equations in differential forms and the knowledge of curl and dot product, okay. So having the knowledge of curl and dot product and vector identities are very necessary for deriving any equations in, electromagnetic field theory. Now let us talk about Poynting theorem, today's topic. See, one important characteristics of electromagnetic wave is that they transfer energy through space when they travel from source to the receiving point. Okay, so they transfer energy. The rate of transfer of this energy can be expressed in terms of electric and magnetic fields strength of the wave. So these electric and magnetic field strengths can be calculated. Do you know that we all know EM waves traveling? Even you can calculate the electric and magnetic field strength when the EM waves are traveling from sun to the earth. So, after talking about EM waves in Poynting theorem, you will be able to calculate those electric and magnetic field strengths or the magnitude of those electric and magnetic fields. Even you can calculate for the bulb. If a bulb is placed 5 meters away from a table and the radiations are coming from that bulb to the table, you can also calculate that electric and magnetic field strength or magnitudes of that EM waves that are traveling. So what are we going to study in Poynting theorem? Poynting theorem is also nothing but, we will be no doubt deriving it mathematically over here. But the basic is that what we are studying in electromagnetic field theory, the traveling of EM waves, the Poynting theorem is the mathematical expression that relates energy transfer and electric and magnetic fields. Okay, so what we can say is, what is Poynting theorem? Poynting theorem is the mathematical expression that relates the energy transfer and electric and magnetic fields, okay, of EM waves. And the amount of energy passing through unit area of the surface perpendicular to the direction of propagation of energy is called Poynting vector. Okay. So what is Pointing vector? The amount of energy passing through unit area of the surface perpendicular to the direction of propagation of energy. Pointing vector, it can be represented, in terms of P also, and in some books it is represented as S. The unit of Pointing vector, if we see, the unit is watt per meter square. Okay. So what is the unit? The unit is watt per meter square of the Pointing vector. So at any point in electromagnetic field, the product of electric field intensity and magnetic field intensity is a measure of rate of energy flow at that point, and that is nothing but the Pointing vector. So we can represent this Pointing vector also as, I'll just write it over here. We can represent this Pointing vector also as E cross H. Okay, and what this E cross H is representing? It is the product of electric field intensity and magnetic field intensity. It is a measure of rate of energy flow at that point. So this E cross H is having a unit that is watt per meter square. Now see, Pointing theorem, it is what we are studying in electromagnetic field theory. Again, I repeat that it is the traveling of EM waves. So Pointing theorem, that is going to represent that mathematical expression that relates energy transfer in space and electric and magnetic fields. And in Pointing theorem, we will also see the Pointing vector. What is Pointing vector? It is the product of electric field intensity and magnetic field intensity. It is a measure of rate of flow of energy at that point in EM waves. And what is the unit of that? That is watt per meter square. And as I said, we after studying this, when we will be, solving numericals, you will be able to see that we can also calculate the electric and magnetic field strength with the help of this Pointing vector and wave impedance of EM waves traveling from sun to earth or bulb to table and so on. So now let us, start deriving with the Maxwell's equation, not deriving with Maxwell's equation, but using Maxwell's equation to derive Pointing theorem. Okay, so what we will do is we shall derive the desired result by using Maxwell's equation. So let me take the pen. Okay. We will be starting with Maxwell's fourth equation to derive Pointing theorem. So what we will write is from Maxwell's fourth equation in differential form. Okay, so we will be writing from Maxwell's fourth equation in differential form. So let us write down the Maxwell's fourth equation, that is del cross H is equal to J plus epsilon del E by del T. Okay, so we have written this Maxwell's fourth equation in differential form. And because now we are not just talking about free space, it can be medium. So we are not taking epsilon naught, we are taking epsilon. So first step to remember to derive Pointing theorem is taking dot product with E on both sides of the first equation. What we get? We get E dot del cross H is equal to, so dot product on both sides, so it is E dot J plus epsilon E dot del E by del T. This is equation 2. Now let us use vector identity to solve the left hand side of equation 2. So using vector identity. So let us see. From vector identity, what we see that as del dot E cross H, if we solve this, what we get is H dot del cross E minus E dot del cross H. Okay. So we are having in this, if we see in this equation, we are having this as a left hand side. So we can rewrite this equation as E dot del cross H is equal to, what is it? It is del dot E cross H minus, okay, I'm substituting the minus sign also. So it will be minus over here and plus, what will it be? Plus H dot del cross E. So now this we can substitute in equation 2. Okay, the value of E dot del cross H we can substitute in equation 2. So let us substitute in equation 2. What we get? Substituting in equation 2. What we get? We get H dot del cross E minus del dot E cross H is equal to E dot J plus epsilon E dot del E by del T. Okay. So say we are driving Poynting theorem, and almost we are also able to see the product of electric and magnetic field that is representing the Poynting vector. So we are in the right direction. Oh, so now let us see. From here, what we can do is we can substitute the value of del cross E. From where we can substitute the value of del cross E? From the Maxwell's third equation. So from Maxwell's third equation in differential form, what we get? Del cross E is equal to minus del B by del T. Or we can write minus mu. What is B? B is mu H. So mu del H by del T. Okay. So this we can substitute in equation 3. The value of del cross E. So we can substitute over here del cross E. So substituting in equation 3, what we get? Substituting in equation 3, we get minus mu H dot, because it is H dot. In place of del cross E, we are writing mu del H by del T. So minus mu del H by del T minus del dot E cross H is equal to E dot J plus epsilon E dot del E by del T. So see, now we are having something in terms of magnetic field and electric field strength. Okay. So now from the partial derivative property, we can write the value of del dot del H by del T as, let us consider, we can write the value of h dot del h by del t as half del by del t h square, and E dot del E by del t from partial derivative property 1 by 2 del by del t E square. Right? See, I can just show you how to solve this. If we see what is del by del t, h dot h. So that is h dot del h by del t plus h dot del h by del t. So what this gives? This gives us 2h dot del h by del t. So what is h dot del h by del t equal to? That is equal to h dot del h by del t is equal to 1 by 2. And we can write this del h dot h as h square. So 1 by 2 del by del t h square. So we are representing it over here in this manner. Okay. So like this, we can even talk about the E dot del E by del T. And now considering these, we will substitute in equation. This is your, just 1 minute. This is your equation 4. So substituting the values of h dot del h by del t and E dot del h by del t in equation 4. Substituting in equation 4. What we get? We get minus mu 1 by 2 del by del t h square minus del dot e cross h is equal to E dot j plus epsilon 1 by 2 del by del t e square. Okay. Then now what is required is we can rearrange this equation. So let us rearrange this equation. If I rearrange this equation, I can write it as minus del dot E cross H is equal to E dot J plus del by del T. I'm taking as common. Over here, I can write epsilon E square by 2 del by del T. I've taken common. So epsilon E square by 2 plus mu H square by 2. So I've written these two terms together, right? Now let us take the minus sign this side. What we get? Del dot E cross H is equal to minus E dot J minus del by del T epsilon E square by 2 plus mu H square by 2. Okay. So now let us further solve it. So take integrating over a volume V, the whole equation. So let us write down the this is equation number 5. Okay. So we are going to take integrating over a volume of equation 5 over a volume V. Okay. What we get? We get from equation 5 volume integral del dot E cross H dV is equal to minus volume integral E dot J dV minus del by del T volume integral epsilon E square by 2 plus mu H square by 2 dV. This is equation number 6. Now using Gauss divergence theorem, what we get? To the left hand side we will use volume integral del dot E cross H dV is equal to surface integral E cross H ds, because the Gauss divergence theorem converts volume integral to the surface integral. So we can substitute this in equation 6. So equation 6 becomes, it becomes what? It becomes surface integral E cross H ds is equal to minus volume integral E dot J dV minus del by del T volume integral epsilon E square by 2 plus mu H square by 2 dV. Okay, so this is nothing but equation number 7. So now let us write down the equation 7 over here properly. I'll take a pen. So equation 7 is nothing but, the equation 7 represents the Poynting theorem, where E cross H represents the Poynting vector. Now let us see what each term of equation 7 is representing. Minus del by del T volume integral epsilon E square by 2 plus mu H square by 2 dV. Okay, so let us see that what each term of this is representing, this equation 7 is representing. See, this minus E dot J dV, this term is representing the power dissipated in volume. Okay, what is this term representing? It is representing power dissipated in volume. Okay, when EM waves are traveling. What is this representing? This is representing the rate of flow of energy. Rate of flow of energy outward through the surface, representing the Poynting vector also, E cross H. Okay, and what is this representing? Power dissipated, okay, in a volume, because minus sign is there. Now let us see this term, the third term, minus del by del T and the whole term. See, what is epsilon E square by 2 plus mu H square by 2? This is nothing but this is nothing but the stored energy in terms of electric and magnetic field. So minus del by del T represents the rate at which stored energy is decreasing, because it is a minus sign, okay, over a volume. So what the whole term from minus, del by del T till dV, what does this third term represent? It represents the rate of decrease of stored energy. So the whole, you can see the rate of flow of energy is also shown in this theorem. The power dissipation when the EM waves are traveling. The E dot J dV represents the power dissipation, and minus del by del T, it represents the rate at which the stored energy is decreasing, and epsilon E square by 2 represents energy density due to electric field, mu h square by 2 represents magnetic, energy density due to magnetic field. Total, these both represent the stored energy, and the whole term represents the rate of decrease of stored energy. So this is nothing but the Poynting theorem. And when we derive Poynting theorem, it is very necessary to write what the each term is representing. Without that, the Poynting theorem will be not completed. I hope you like the video. So this, you can just follow with the reference. Thank you, students.